You remember we covered direct numerical simulation last sessions, and starting from today, we're going to talk about large eddy simulation. So, as the name suggests, it's another simulation method. It's not a total modeling approach. And by simulation, we mean that we do have to resolve relevant time and spatial scales. But in LES, unlike DNS, we don't have to resolve everything. So um we might say that we have larger three-dimensional unsteady turbulent motions which are anisotropic, geometry dependent, and contain most of the energy. Um, these will be directly resolved, whereas the effects of smaller scale motions, which more or less have a universal character, are modeled. Uh, the larger eddies uh, highly depend on geometry, and we know this. And modeling an isotropic geometry dependent structure is very difficult because if you're able to model one problem, when you go to another slightly changed geometry in another problem, then the model won't work. And the idea is okay, let's not model the larger structures, let's resolve them, but then, when we have the universal eddies that are not changing from geometry to geometry, let's develop some universal model for them. And the problem arises here, and it's that those small eddies have a significant contribution to the energy dissipation in the cascade. You know this. The dissipation comes from the dissipative eddies. And there is a significant physical process going at the dissipative eddies. So you should be careful to develop a model that can truly reflect the correct physical dissipation. So there are also different variants of LES, like detached eddy simulation, DES. And it's a kind of hybrid unsteady runs and LES method, wherein close to the body, the solution is calculated using the unsteady runs model, and far from the wall or far from the body, the LES equations will be solved. And there is an intermediate region in between where the solution will be a mixed type. So when you hear detached eddy simulation, it's kind of a hybrid model, hybrid solution. Here I wrote some other characteristics of LES, and the first one is that it is very good for flows with large scale unsteadiness. For example, for bluff body wakes, where the wakes are dominated by large structures, or for the airfoils at a very high angle of attack, like 45 degrees, where the flow is massively separated. There will be huge eddies dominating the flow field, and the LES is very perfect for this. In terms of computational expense, LES lies between Reynolds stress modeling, RSM, and DNS. So we will talk about RSM later. So these K epsilon, K omega, and these modelings, which you might heard before, these are faster than RSM, Reynolds stress modeling. But Reynolds stress modeling itself is the most in intensive computational cost of RANS modeling. So what Reynolds stress modeling do is that it models all the stress components inside the Reynolds stress tensor. You remember the Reynolds stress tensor with all those nine components, and You had to have these six components of the Reynolds stress because it was a symmetric stress. So what RSM does is to model all these six components of the Reynolds stress tensor. We have to also understand that the equations we are solving in largely simulation are also for the instantaneous flow. Okay, so the Rance equations, you remember, they were for averaged fields. If you compare Rance, LES, and DNS, there is one significant difference. In Rance, we solve for statistical averaged fields, the bar sign you see everywhere. In DNS, we solve for instantaneous fields, and in LES, we solve for filtered instantaneous fields. That's the fundamental notion under LES. So the concept tells you that you have to resolve large scales and model remainings. I mean, model the smaller scales. So you have to separate large and small somehow. How do you separate, for example, large and small in your kitchen? If you want to separate large and small things in the kitchen, you use a filter, you use elec. It's exactly what you do in LES. Depending on the size of the filter that you use, you can separate the scales. This filtering will be done in a mathematical way, although. So you don't use physical filter, physical elec. You use mathematical relations. So there are four conceptual steps in LES. Number one is the filtering operation. When we say filtering, we refer to filtering in space, spatial filtering. So we are talking about sizes of eddies. And this is in fact what we call a low pass filtering operation. What I am trying to do is this. I have a momentum equation, for example, and I want to derive a new momentum equation that will apply only to the instantaneous fields generated by the large eddies, only large eddies. Of course, since large eddies are affected by small eddies, there will be some extra terms in the equation which hopefully those extra terms, we hope that they could mimic the effects in an accurate way. So this forces me to derive new set of governing equations written for the instantaneous filtered fields, not only instantaneous fields. Originally, for example, I have the like uh, velocity field like this. U is a function of space and time, and this function, this velocity field, which is a function of a space and time, um, can be written as a combination of a filtered or resolved velocity field, which I am showing by tilde, u tilde, and the part that I call it residual velocity field, or I call it, in LES we call it subgrid scale, or SGS, subgrid scale, SGS component. You have to note that all of these three are three-dimensional. They are, you see time in here. They are time dependent. They are instantaneous fields. Okay, what I mean by instantaneous is that if you just um, take a snapshot of one realization, they are instantaneous. There is no such average thing like in Rance, what we did in Rance. There is no similar story. So, in order to have some feeling about the filtering, um, I can refer you to the filtering operations on, for example, images. You probably have heard about those filtering operations in MATLAB, the Gaussian filter, median filter, and etc. So it's a good point that we have a look at these filtering things right now. So the first thing is to look at the images as functions. So to better understand the inherent properties of images and the technical procedure used to manipulate and process them, we can think of an image which is comprised of individual pixels. Digital image has some pixels, and we interpret this pixel as function f, and each pixel also has its own value. For a grayscale image, for example, you see this grayscale range in here. Each pixel would have an intensity between 0 and 255, right? And the 0 is being pure black, the 255 is pure white. So I can write f of x and y uh, that gives me the intensity of the image at pixel position x and y. So I have a two-dimensional image. This is x-axis, this is y-axis, and these are certain pixels. So f of this x and this y could be, for example, 164. So it means that it's somewhere in here. It is a gray color with code 164. So on the other hand, I have a color image, and a color image is just a simple extension of the uh, grayscale image. So if f of x and y is um, now is a vector of three values instead of one value. If you use RGB image as an example, red, green, and blue RGB, the colors are constructed from these combinations, R, G, and B. Therefore, each pixel of the image has three channels, three values, and it is represented as a 1 by 3 vector. And since the three colors have integer values, again from 0 to 255, which means 256 numbers, you have 256 to the power of 3, which is nearly 16 million. So this is 16 million colors, for example, RGB image. And as an example, you're seeing that, okay, this pixel has these three values. This is for the red, this is for the green, and this is for the blue. And again, this pixel in here, 0 means it has no green inside. So it's a combination of red and blue only. And when you understand these filtering operations, this will help you very good in order to understand filtering operation and processing images in LES as well. Now let's talk about the image processing. There are two main types of image processing. First one is image filtering, and the second one is image warping. Image filtering changes the range. Okay, in other words, it changes the pixel values of an image so that the colors of the image will be altered without changing the pixel position. But in image warping, the domain or the pixel position will be changed. So the points will be mapped to other points without changing the colors. The goal of using filters is to modify or enhance image properties, or sometimes to extract valuable information from the picture, like extract the edges, extract the corners, extract blobs. And in here you are seeing some examples of what applying filters can do to make images more visually appealing. For example, denoising. You have some noise in some images, and then you denoise it and you will come up with a smooth image. Or you can mm, do super resolution on image to enhance the quality or resolution of the image. So you have this image and then you will come up with the super resolution image. We have two commonly implemented filters. One of them is moving average, and the other is the image segmentation. What is the moving average? Moving average actually replaces each pixel with the average pixel value of that pixel and neighborhood window of that pixel. So you see it in here. For example, you want to do operation of moving average on this pixel in this image. It means that you have to get the average of all of these 10 pixels and put the desired value in the same position of that pixel. This is the moving average operation. So, of course, the effect is more smooth image with sharp features that is removed, right? If you do the moving average. If you use, for example, this is a 3 by 3 neighboring window. So you use that if you have this original image like this, and as I said, I use a 3 by 3 uh, mm, window, neighboring window. Average means 1 over 9. I have 9, let's say, values in here. 1 over 9 of these. So when I take the average of these 9 and put the result in the central pixel, I will have I will get a blurry image with a box filter or moving average filter. Box filter is another name for the moving average filter. So this is, for example, for grayscale images, and actually, this is exactly happening to the velocity field when we want to do LES. You're seeing three different images in here. The first one is the DNS data and of a homogeneous turbulence on a domain uh, which is a cube with length L. You remember this cube. So this picture is just a cut of the cube at some place, okay, and it is frozen in time. So it is a snapshot of that homogeneous turbulence inside that cube. So when you do a box filter or a moving average filter on this, you will get, for example, this one. This one is obtained with a filter size with L over 32. So the filter size in here is L over 32. I mean, this square that you are using in the filter, in the moving average or box filter, the size of this is L over 32. And if you do it once more, for example, with filter of L over 16, so it means that your filter is twice larger than the filter in the previous step. You see that you are ending up with a much more blurry image. Okay, the details are gone. So exactly this is what is happening in LES. In LES, you are seeing mostly these kind of details instead of the very fine details like in here. So I have a snapshot. I have DNS results that is very detailed. This is the DNS, detailed DNS. And you see that all eddies are resolved, everything is included. But when you filter it out, you only see larger eddies. So what I'm trying to say is that this only belongs to one snapshot of the field. This only is the U prime, and this U prime which is the residual, is not a fluctuation anymore. So don't forget that this is not averaged and this is not fluctuation. These are completely different things. It's the difference between the actual and filtered field, the residual field. And what I mean by SGS, subgrid scale, when you're numerically trying to solve the equations in LES, your grid has a certain resolution and it will be able to resolve some large scales, but it cannot resolve the other smaller scales. For example, if you have a field like this and you put a grid on this field, probably you remember that in order to resolve a vortex, you have to have at least uh, four grid points in order to show one vortex, like this vortex that I'm showing to you. So this is a representation of, changed my color. This is a representation of such a vortex in your field, right? So depending on the size of the pixels or size of the grid that you put on this field, you you are able to resolve until some point. And what happens if you have a vortex that is smaller than your grid? What happens when you have this vortex and this vortex is inside one cell in your grid? So you cannot resolve it. If you want to resolve this, you have to divide it again into four squares. So at until some point, your grid actually gives you the ability to resolve the vortices, and after that, you cannot resolve them. So this is where the subgrid modeling or SGS comes into play. For these scales, for these smaller scales, you don't resolve them, but you model them, and you call them subgrid scale. Subgrid means it is smaller than one grid. The scale is smaller than one grid, so you have to model it. That's the first conceptual step in LES, and we said that it is a filtering operation. So you do filtering just like you do filtering on images in MATLAB and everything. The second step is to obtain the governing equations for U tilde. What was U tilde? Once more, U tilde is the filtered, instantaneous filtered velocity. So you use Navier-Stokes equations and you obtain the governing equations for U tilde. Now we need a new set of governing equations for filtered velocity, because when we do the filtering, we are losing the details. Like in here, you see the details in here are much less than the details in DNS or a real data. Because we are losing the details and we know that they have an effect on the larger structures, the smaller structures, they have effect. They do have effect on larger structures. So we cannot just ignore the smallest details. They affect the shape and also the size of the large eddies. So, how should I reflect these effects in the equations mathematically? When you derive the governing equations, meaning that you're replacing in the Navier-Stokes equations, you're replacing every u with u tilde plus u prime. This is filtered, this is residual. What you get is, when you do this in the Navier-Stokes, what at the end of the day, what you get is the residual or subgrid scale stress tensor. Again, You can compare it with RANs. In the RANs, you will get, um, it kinds of reminding you the RANs derivation, but physically we are representing something else. In fact, I will shortly show that the stress definitions are completely different in LES and RANs. In other words, SGS, a stress tensor, and um, Reynolds stress tensor are two different worlds. They cannot be compared. Okay, after you obtain the governing equations, what will you do is to model the SGS stress tensor. Since we have some extra terms, like in RANS, you remember in RANS you were writing u bar plus u prime, and then when you put it inside Navier-Stokes, some extra terms will show themselves, and we call them Reynolds stress tensor, ui uj prime. You remember these. The same thing happens in LES. When you do this, you will get SGS stress tensors, and uh, you have to model them, just like similar to Reynolds stress tensor that you try to model it. So you have to model SGS stress tensor as well. And this term is, in fact, a mathematical term that reflects the physics of smaller eddies that I was talking about. So those effects of smaller eddies that um, we cannot resolve them, the effect of those are in this tensor, SGS stress tensor. How they, for example, interact with larger eddies, and more importantly, how they dissipate the energy. Okay, the fourth step is to solve these model filtered equations. And when you solve those equations, because you wrote the equations for u tilde, you find u tilde. So once you have appropriate SGS stress tensor, you can solve equations and get u tilde. But you have to note that you still get one realization of the flow. So it is still a snapshot. It is time dependent. It is instantaneous. Since in largely simulation we are resolving a significant amount of eddies, there are also, uh, the procedure is very computationally intensive. For example, there is a, I don't know, I had mentioned it before or not, there was a combustion chamber, 400 milliseconds of the LES simulation, and it took 1 year of a computer run, for example, just for zero point 0.4 seconds of simulation. So these are the four steps you have to follow to obtain the proper mathematical framework to start simulating in the sense of LES. Uh, the works related to large simulation, as far as I know, is still low in our country, in Turkey. And okay, I'm not a numerical person, but if I was, I would have studied large simulation. This also applies to the industry, not only in the academia, because solving with RANs based models is not enough today, and because RANs based models, they oversimplify the problem. Uh, but not every engineering problem requires LES. I accept this, but as our country develops and has more ambitious aerospace projects, we start to deal with more complex flow problems and complex geometries. So you should be aware of this after you're done with this class. So hopefully some of you in your future will work on LES, or mm, you will be a numerical guy and do something else, DES or LES or something.